Today we are addressing a crucial operational issue in blast furnace iron making, the care of scabs in the lower furnace. This unmolten material accumulation poses significant challenge to furnace stability and efficiency. We will cover their nature, causes, and how we prevent, detect, and manage them effectively. Coming to our next slide, which is about understanding a scab with respect to location and detection. First, let us define scab. They are unmolten body material that fail to melt in time. They typically form in critical lower furnace area, especially in front of tuyeres. You might also find cohesive material in the cohesive zone at the wall area or wash belly. Visual cues include a tip tuyer appearing oval instead of round if a scab is resting on it. We rely on tuyer pip sights and cameras for direct observation. Additionally, differential pressure delta P over the two-year stock can signal blockages, and monitoring a step temperature can indicate localized cooling due to adhernesis. So, in case of such things happens, and if the two-year physical look or the cameras signal something like that, we can correlate with the step temperatures also to corroborate the findings. Coming to our next slide, which is about the primary causes of scabs, and there are root are many. Body and thermal control supposed to be one of a very important aspects in this. Understanding the root causes is also always important in which is we can say it is key to prevention. A major factor is poor burden quality and permeability, often due to excessive fines, and fines, especially the material less than 5 mm in the ore burden. These fines reduce gas flow, impeding proper heating and reduction. Similarly, suboptimal softening and melting properties of burden can cause them to melt too slowly or at lower temperature, creating impermeable layers. Thermal instability, particularly a very cold furnace or a chilling trend, drives the cohesive zone downward, potentially solidifying it at a two-year level and forming a scab. Late warming up of burden influenced by low burden levels or poor gas permeability also contribute. Coming to our additional factors and operational impacts beyond burden and thermal issue, other factors uh, exacerbate the scab formation. Inadequate or uneven cook layers allow ferrous layer to contact, forming thick impermeable zones. High level of alkali and zinc in the burden are also known to promote adherences. Excessive moisture input from the raw material or injected prolonged drying, potentially shifting reduction zones and causing irregular burden descent are the uh, primary causes. The consequences are severe. The scab can cause tear tipping, damage, or complete blockage, leading to PCI backup and explosion risk if coal injection continues into a blocked tear. Ultimately, scab disrupt smooth burden descent and contribute to overall furnace chilling and instability. Coming to our uh, observation, as it is already shown how the pepsides signals many times, and it is also easy tool to uh, corroborate these findings. Coming to the prevention strategies, the proactive prevention is paramount, and we must prioritize optimized raw material and burden distribution. This means aggressively minimizing fines through screening. We select burden material with ideal softening and melting properties and maintain adequate coat layer, especially at the wall. Controlling alkali, zinc, and moisture input is also critical. Operationally, we strive for optimal gas flow distribution, avoiding peripheral flow, and consistently manage the upward force from gas pressure. Crucially, we ensure consistent and systematical PCI injection across all tier with system to immediately shut off PCI if a blockage occurs, maintaining a stable stock line, a consistent stock line, and overall thermal stability prevent chilling, tend that foster scab formation. Now, coming to the managing existing scab is the very important activity or execution for blast furnace operators. The question rises, should scab form despite our best effort? Timely management is essential, and these only form when we uh, delay in our action. Remedial action in managing this scab include adjusting burden distribution and gas flow to the affected areas. We also employ thermal flushing technique using low melting, high fluidity slag, sometimes with an additive like a FeO or CaF2 to help melt and dislodge adherences. In some cases, lowering the stock line, a cleaning action can assist in dislodging them. Temporary reduction of blast volume or plugging a specific tier can also be used, but with cautious uh, approach. In conclusion, managing a scab in the lower blast furnace is complex and continuous task. It demands a holistic, proactive approach focused on raw material quality, precise operational control, and vigilant monitoring to ensure a stable, efficient, and safe blast furnace operation.